Hello guys, today I'm going to go over Weld, and we are going to look at the stresses that develop in welds and then how we are going to analyze stresses in welds. So you use basically welding if you don't want to use obviously bolting or riveting different joints, and then it's a very efficient way of and a cost-effective way basically for connecting mechanical parts. And in the case of welding, let's say you have these two parts. If I was trying to basically weld these, obviously I'm going to start putting weld on the inside, and then you keep basically doing several passes, and then ultimately the weld is going to look like this. And the weld is going to be characterized here by the leg length. So when you specify the welding on a drawing, basically you're going to give it that weld length, and then the guy is going to go up that distance here and then that distance here, and he's going to basically join them. So it's going to basically look like this triangle. If you look at this from from the side, you are going to see this, and like I said, Z is going to be your leg length, and then you have one leg length on this end. So, and this triangle basically is an isosceles triangle, and basically what we are going to do is we are going to identify this throat length, and the throat length is the shortest distance inside this weld, and because usually most of the time Z is going to be equal to Z on this end, this guy is going to be a 90 degree, and then this guy is going to be 45 degree. So I can basically get the throat length from the leg length, and the throat length given by H is going to be equal to Z times cosine 45, which is 0.707 Z. Right now, the area, right, that is along the middle here, right, all the way through, is going to be equal to H multiplied by length, where length is going to be the length of the weld, right? So as long as the weld, you are basically going to get that out. All right. So when we are analyzing welding, we are going to look at the shear forces, right, which are, or the shear stresses, which are going to develop here, and primarily we are going to look at the shear stresses along the throat area. So there is really no exact analytical equation for evaluating the stresses except this, right? So we're only going to be looking at the throat length and the throat area, obviously. Okay, so I'm going to start discussing what we have in our presentation, and I'm going to share my screen now, and that would basically be chapter 9 in our presentation. So this is what I just mentioned earlier. So you have two plates, and on the weld you are going to specify the leg length, and the throat is going to be the shortest area over here, and then the top of the weld obviously is it would basically be called, usually referred to as a toe, and this corner is the root of the weld. So root of the weld, toe of the weld, this is the throat length, and then this is the leg length. The way the weld is specified on a drawing, in the case of you have a plate, vertical plate and a horizontal plate, it's going to be specified like this, and this 5 is essentially the leg length, right, which is in this case the distance between the leg length, which is here, right? So this is your leg length, and that would be symmetrical, meaning you're going to have leg lengths on all ends of here. Okay, and in the case of putting multiple welding, it's going to be specified like that, where you put 60 in this case is going to be the width of the weld, and then 200 millimeter is the intermittent distance between the center distance of the welds. So we won't really be using that, but we will be maybe in some homework assignments they will tell you that you're going to have like different types of weld, but obviously it should be illustrated on the drawing very properly. In the case of welding a tube over to a flange, you're going to use this circle, and that circle basically indicates that you have 5 millimeters. I want to zoom in on here. Okay, no, that's not okay. Okay. In the case of a circular weld, basically what we're doing is you're going to specify this leg length or 5 millimeter, and then that 5 millimeter is going to be throughout along the flange. right? And then if you are looking at a top view over here, from this end, you are going to see that this weld is gonna be looking like that. Okay, so it is pretty basic like now, getting that throat and from the leg. Regarding different types of welds, this is called a butt weld, basically, or square butt weld. Basically, you have a square and then you're going to put welds on both ends. This is called a single V or V weld, basically where you specify the angle that you are going to be filling these two parts with. And this is called a double V, right? Which makes sense, right? So you're going to put weld on both ends, and then the last one is single bevel, where basically you are putting weld along this this guy. So so these are basic drawings, and then there are obviously different ways for specifying welding, and you know, we are going to be dealing primarily with basic throats that you are going to see in the examples that will follow. So this is a case of this you know, butt weld, and what we have here is that we have a force applied axially, and you are going to have the axial loading. In this case is going to be F divided by the area, or the throat in this particular example is, like I said, the shortest distance that is subject to the stresses, and in that case the throat is going to be this here, this length H, and the force or the stress is going to be F over HL, and in the case of a shearing, again we are going to be using this F over HL. All right, so regarding the welding of different types of plates, for thick plates usually it's recommended to you can use this type of welding, or this is called a U joint or a J joint, and these are typically used for thicker plates, either this configuration or these two configurations. For, you know, weaker configurations or sheet metals, one way to do is you can use this corner weld, and this particularly is used on sheet metals, where basically you bend one plate and then you just give it a small distance so you can essentially weld on the top, right? And this is usually done for sheet metals. A transverse fillet, basically, or fillet weld would look like that, and this is going to be your axial force, and then that is your throat. So the area here again is 0.707 H, and we can basically get our stresses. And like I mentioned earlier, there is no exact analytical approach that would tell you exactly the stresses. The standard approach is to ignore the normal stresses, and we only consider the shearing as follows. So in this case, we know we have this force F, and then we have the shortest area, or the smallest area is a throat area, which is this, and you are directly going to get the shear, and then you're going to simply shear. The shear is going to be equal to F divided by the throat area. All right, and here, you know, notice that they are not doing projection of the force on the area. So this is given to you like this, and then you have to use it like that in the case of later on in the exam, or if or on the project if you have to deal with welds. All right, again, you're not projecting the force on the area. You are simply saying that the shear inside the weld is going to be equal to the force divided by the throat area. Same thing applies over here, right? And then here it's basically more relevant. Why? Because now the force is actually in line or parallel to that throat area, and in that case, obviously your shear is going to be equal F divided by the smallest area in the weld, which is again here H times cosine 45 multiplied by L. All right, so this is, you can see here it's applying to like basically pure shear force, and again here this is also a pure shear force, right? And here obviously that force has some normal component, right? But we're not taking that normal component, and then we're not even projecting the force on the cross section. We're directly providing it like this. Okay, and I think right now when we do the example, you're gonna understand that much clearly. And here's what we have. Let's look at this example. So we have a bar right? And the bar is connected to a wall, and the welding is circular. Basically, it means that it is throughout, and 5/16 is going to be your leg length, right? So here, okay. So basically, you have, let me draw this actually. So you essentially you have weld throughout here, and then there, and then you have also weld over here, right? And also you actually have weld on the inside. That force is over here, so we know you're gonna have. So I'm gonna actually draw the last one, which is here. Okay, and if you are trying to get the shear stress applied over here, then the shear is going to be the force divided by the throat area. So what is the throat area? The throat area is going to be equal to these four areas, right? So it's going to be 0.707 multiplied by the leg, and you're going to multiply it by the perimeter of this. So this is going to give you this whole area of, or the smallest area inside that weld. So 0.707 multiplied by 5/16, right? And then multiplied by the perimeter of this, which would actually give you the throat area. Then the shear on this weld is simply going to be equal to this force, which is 32 kips, 30,000 pounds, divided by the area. Therefore, there you go. Then this is your shear on the weld. Okay, so again, this is your leg length. Okay, let's go to another example, and then this is a case of torsional stresses that occur in welding. And here what I would like to do is, let me make a simple drawing to explain that further. So here what we have is, we have a beam, and the beam is connected on the wall, but instead basically you have two thick welds on the top and on the bottom, right? And how are we going to analyze that? So the way we're going to analyze shear in or torsional stresses in weld is going to be very similar to the way that we analyzed stresses inside or on bolt groups. And the way that this would work is, let me share my video, and I'm going to stop the screen for a second. Stop the screen sharing, and then okay. All right, so in the case of a torsional stress is applied on a weld, let's say you have a beam, and that beam is connected on a wall, let's say, and what you have is, you have like welding over here, and you also have some weld over here. And let me just make it like that, and let's put some weld over here, right? And let's say this is going to be your force. How do you find the shear stresses, right, which are, let's say, on this point, right, or this point? So the way we're, like I mentioned, the way we're going to do this is, we're going to treat it as if this was a bolt group. So the first thing that, remember, in the bolt group, we found the centroid of this, right? And I'm going to actually put it here. And how do you find the centroid? You're going to say x of g, right, is going to be equal to, let's say this is, area A1, A2, A3, A4, right? So each one of those is a different area, and then each one basically has a coordinate, right, about it for its center. And then obviously we're going to have to establish a coordinate frame. And let's say here your coordinate frame is at the bottom, right, x and then y. So xg is going to be equal to A1 x1 plus A2 x2, etc., and then divide this by A1 plus A2 plus the rest of the areas, right? And then in a similar approach, you can get YG is going to be equal to A1 Y1 plus A2 Y2 plus etc., and then divide that plus the areas, right? So this would, you can basically, based on, and this is obviously a very general, but in the case of a drawing, you should be able to clearly identify where the center of these welds are, and you can get the centroid of this. So this is your G. Now I can basically get the moment, and then the moment is going to be F times L, right, where L is going to be the length from here to here. So the moment is going to be equal to F times L. And the loads that we are going to have applied over here is you are going to have a single shear applied everywhere on the weld, right? And the total area of this is obviously going to be equal to, let's say, A1 plus A2 plus A3 plus A4. And you're gonna have, just like what we said earlier, you're gonna have primary and then secondary shearing, and then the primary shearing is gonna be caused by the shear forces F over A total, right? And then net shear stress is gonna be everywhere, right, on every element. So you're gonna have T prime everywhere, and you are going to have tau double dot, right, which is, as you guys remember, and that is gonna be MC over J, right? Or M is a moment, basically. C is going to be what? C is going to be the distance from that point G to the point that you're analyzing. Let's say you're analyzing this point, then this is going to be your C, right? Or R, some people call it, right? J is going to be your the polar moment of inertia for this cross section, right? And this cross section obviously is made of different elements, and I'm trying to get the J. So there are two ways of getting J. One way is, which is what I'm going to show you right now, right? Analytical. And the other way is based on a table, right? Where you basically calculate based on JU, and then JU is going to be looked from a table. Let's first go over the analytical method, and then the other way is going to be based on JU. So based on a dimension of this cross section, I should be able to find the analytical polar moment of inertia, or based on a table, which what I'm going to show in a second, we're going to basically find J based on this value JU, which we are going to look from a table for standard welding designs. Okay, how do you calculate the analytical polar moment of inertia, for example, in the case of, let's say you have something like this, right? Some, random cross section, and then this guy, right? And let's say your G is here, and let's say this guy is, A1, and then this guy is B1. Let's say this guy is here, A2, and then B2, right? A2 is obviously the length of this guy, and then that. How do you do that? So the polar moment of inertia J is going to be equal to Ix plus Iy, I'm sorry. So in the case of a, circular cross section, this is your x-axis, and then as your y-axis. We knew that Ix is going to be equal to pi over 4 c to the power 4, and we know that Iy is going to be equal to pi over 4 c to the power 4. So J is actually equal to Ix plus Iy, which is why it is actually pi over 2 c to the power 4. Okay, so when you are calculating the polar moment of inertia, you have to add the area moment of inertia on both ends, on the x direction and then in the y direction, and then this will always give you basically J. How do you apply this over here? So we are going to find J about the centroid of each one of them, and then we are going to use parallel axis theorem to connect J about the centroid for this element into here. All right. So obviously I need to know this length here, R1, and I need to know R2, right? And what is Ix1? So or let's see, actually, so let's call actually JC1, right, which is the polar moment of inertia for this element about its center, and then JC2 is here, where this is point, let's call it C2, and then this is point C1. So JC1, right, is going to be equal to what? It's going to be equal to 1 over, we know Ix for a rectangular cross section is going to be 1 over 12 A1 B1 cube, right? So this is your Ix. Now Iy is going to be plus 1 over 12 B1 times A1 cube. So we're done with JC1, and then how about JC2 is going to be equal to 1 over 12 A2 B2 cube plus 1 over 12 B2 times A2 cube. So now you found the polar moment of inertia about the centroid of these elements, or these welds. You want to map it over here. You're going to use parallel axis theorem. So J about G is going to be equal to mapping the first one, so JC1 plus the area of this one, right, which is equal to A1 B1, right, multiplied by the length, right? R1 square, right? So this is your parallel axis theorem, and then again, this is gonna appear right now in the notes, plus JC2 multiply plus the area, the second area, using the parallel axis theorem, so B2 times A2 multiplied by R2 squared. So this JG basically is going to give you that polar moment of inertia, and now we can use the shear is going to be equal to the moment, right, at the weld, right, which is what I just described earlier. So the moment at the weld, right, multiplied by C or R in this case, right. So if you're, you can easily use C or R as a distance from the centroid to the moment that to the point that you are trying to analyze the stresses. So M times C divided by JG, right? And this is pretty much all that you need to do in order to evaluate the stresses on here. So obviously here we are going to have, and this is, by the way, the secondary shearing, right? So this is your secondary shearing, and then the primary shearing was equal to the force divided by the area. Okay, let's come back to our notes, and all right, so like I said, so in the case of when you are looking at the torsional stresses, that force is going to result in primary shearing and then secondary shearing, which is what is due by the moment, right? So ultimately, you need to get that total shear, and then one way to do that is you can decompose the secondary shearing into X and then Y components, and then here, obviously, it's going to be in the Y component, so you just add the Y components alone, and then you add the X components alone, and then you can do the square root of tau x squared plus tau y squared. All right, so this is what I just described earlier. So primary shear is this, secondary shear is that, MR over J, and A is going to be the throat area, right? In the case that the one that I just showed you, so the area is going to be simply the area of the weld, which was A1, B1 plus A2, B2, right? And our just previous one. Okay, so let's look at the other way of evaluating J. And one way we can actually use a table. And when we use a table, we can use this formula, which is J is going to be equal to, this is a total moment of inertia. Polar moment of inertia is going to be 0.707 multiplied by H multiplied by Ju. So let's also look into that. So this is what I just described earlier, right? You can get your J like that, JG1 plus A1 R1 squared. So this is a parallel axis theorem mapping first element into this point, and then again, this is for the second element in this. So that is pretty basic. The other way using the table is, turned out that when you are using, or when you are doing a weld, most of the time, basically, you are going to use basically standard design, right? Let's say you are connecting a rectangular beam, for example, right? You're going to basically put two lines, right? And then this line over here, or this drawings over here, basically, it's really simplifying how the weld would basically look like on the actual part. I'm going to zoom in. So let's say your weld looked like that, right? It was a line weld, right? And to draw this, so this guy is like this, right? So let's say you have, this is your beam, right? And then this is the wall here. And let's say this is your force. Okay, so the first case is basically you have weld on, let me change the color over here to this. And okay, the first one basically is the weld is over here. This is what you have, right? So this one corresponds to this case, right? And on the drawing, basically, they would give you the throat length, right? Which is H, right? I'm sorry, the throat thickness. H, or the leg, I'm sorry, they would give you the leg. Apologize. So they give you the leg, and the throat area in this case is going to be simply along this line, right? Which is 0.707 times the leg, multiplied by D times the length of this guy. So you have D multiplied by the leg multiplied by cosine 45, which is 0.707. Okay, so this is in the most basic design, and then location of the center of gravity, right, is going to be at D over 2, right? So in this case, Ju, right, which you are going to use, is going to be equal to D cubed over 3, right? And when you are getting J, you don't use JU, right? Remember in the previous slide? Let me come back to the previous slide. Okay, I'm not sure why it's not zooming out. Okay, there you go. So the value of J, right, which you are going to use in a secondary shearing, it's going to be equal to JU, but you have to still multiply it by these. Okay, so the value that you get from JU in this table, so this value, you're going to multiply it by 0.707 H times D. No, I'm sorry, H times H, right? 0.707 times H. And that's it, right? So you just multiply the JU by this value. All right, so let's say you actually have 2 lines, right? So what you could also choose is you could, for example, want to have another line over here, right? And this line is on the back, right? So this is behind the plate. So in that case, basically, you just done that, right? And if you have done that, then obviously the area of the weld or the throat area is going to be equal to this guy times 2, which is going to be this. And you would use the throat area when you are calculating the primary shearing, right? When you are calculating tau prime, which is the force divided by this area. Now, if you are trying to calculate, the secondary shearing, obviously you need to get JU, and then JU is going to be provided to you directly here, right? So D is going to be that distance, and B is the distance between them, right? Which is B, right? The distance between these 2 welds, and then that's it, right? So multiply this guy by 0.707 times H, and you've got your J. So when you have your J, you can get your secondary shearing at this point, this point, this point, or this point, right? And then I'm going to draw my secondary shearing. It's going to basically look like that, like that, like that, and maybe like that over here, right? Because your moment of your centroid is essentially located on the inside. Okay, how about in this case? In this case, basically, let's say you have the welding at the bottom of the plate and then the left side. Again, now you are going to have, this is going to be your throat area, and then this is going to be your JU, and then etc. Okay, this is in the case of a circle. This is a case of a full weld. Basically, you are doing it, all over. And this is for in the case of a C channel, for example, where you choose to basically put the welding on the side. So, the idea is pretty basic. You just identify the type of the weld, identify the design of the weld, and then you identify the throat or the leg from the drawing, right? And then it is really a matter of you identifying, which looks like the weld that you are dealing with, and then you get your primary shearing, you get your secondary shearing, and then you can get a total shearing. All right, let us work on this example, and then that would be it for torsional welds. And here what we have is we have this C channel, and then that C channel basically is being held by this part, right? So the part here is you have this, cylinder over here, right? And this plate right there. Let me actually try to draw a 3-dimensional figure of this. So essentially, this is what we have over here. So we have, this is your C channel. Okay, this part right here is this. Okay, so here you're looking at this guy from, so this guy is this view right there, right? Okay, so this view, you're gonna see that. And you guys know if it was a C channel, basically, this guy is gonna have a little bit of a wall to it, right? And that is gonna be this. All right, and on the top, this guy is basically constrained in this this part basically, and I'm gonna actually draw this part here, and let me change the color. And so this part is housing this guy on all ends. So this guy is gonna look like that, right? So it's here. it's here, here, and it actually goes like that, and like that, and like this, and like that. This line right there is basically that tube, and this is like this. So there's that tube right there. Okay, just delete this. Okay, so this is what we have, and essentially, and I'm gonna draw right now the welding, and I'm gonna draw it in black. So so we have the welding is throughout. So from here, right, we have a welding, right, throughout, right. So this guy is mirroring this end, and then this guy is mirroring this end. So you have a weld whose leg is 6 millimeters, right? So we have, so this guy right there is actually here. Okay, so this is your 6 millimeter on here, and then this is the one which is on the other end is here, right? And this guy right there, right, on the right side is going to be on both ends on the inside, right? And that basically means you have weld here, and then you also have weld here. So again, you have it here, and I'm going to show it that in dotted points because we can't see that. Okay, so this is what you have, and essentially the force that is applied on here is applied throughout this. So this is a 50 kilonewton. So each one of those is going to see a 25 kilonewton, just like what you see in the below diagram. So the force is coming like that, right? And that force is 50 kilonewton. Okay, so we have 50 kilonewton applied on both ends, and you have 25 kilonewton applied on this weld, and then 25 on the other weld. And looking at that, we know that this is what? This essentially look like a C-type weld, right? From the diagram that we have above. And essentially what we can do over here, we can get the cross-section, or we can get the centroid of this weld, which is going to be probably somewhere here, right? This is your centroid. And we're going to get the moment of this force with respect to the centroid, and then this centroid basically is going to give you, secondary shearing like that, and then it's going to give you primary shearing horizontal, right? So it's going to be, okay, let me read through this one last time. So an element over here is going to see, and even I would like to actually plot that in blue, right? So your primary shearing on this element right there is going to be this, right? And then secondary shearing is going to be like that, right? This is on this element, because your moment is like this, and this guy is going to be your secondary, and then this guy is going to be your primary. Okay, so that is it. So I'm going to actually clear this drawing. Okay, and now we can go from here. So the first thing that we have to do is we have to get the location of the centroid. And the location of the centroid, so this is what I have in my, this is from this, right? This is your C channel, right? And then the C channel is going to provide us the location of the centroid relative to the weld. And then we're going to add the offset that we have from the force to the weld. And that is it, right? So first of all, we got the throat area, right? So we're going to use the throat area for the primary shearing, right? And from this diagram, basically, this is my X bar and then Y bar. So X bar in that case is going to be the distance from the weld to point O, which is in our case this P squared divided by 2B plus D. And then Y bar is obviously D over 2, which is half because this is symmetric. And this is my JU. So JU, I will simply apply the equation that is provided to me. All right. And this is my, looking at this again. So my moment is going to look like that in that case, right? So my moment, this is my primary shearing is going to be throughout. So tau prime A is equal to tau prime B is equal to tau prime C is tau prime D. And then my secondary shearing at A is like this, perpendicular, obviously, to this radius. All right, so now we just have to crunch the numbers and then get the shears at the various points along the weld. So this is what you are also expected to do in the case of your project. So first of all, we're calculating our primary shearing, V over A, right? We got our throat area, right? Where 2B plus D is equal to what? So here, let us first of all identify what B and D are, right? B is going to be this distance, and then D is going to be the larger distance, right? So in our case, what is B? B is equal to 56 millimeters, right? And then D is going to be equal to this 190, right? So B is equal to 56 and D is equal to 190. So you just get your area and then you get your primary shearing, pretty basic. And then the second part is to get your secondary shearing, which is MR over J. Just apply the equation here, 0.707 H times JU from our table. We can get our JU, which is what I just so first of all, we're gonna calculate our X bar and our Y bar, right? And to be able to get that total moment, right? So this is your X bar, Y bar, and then JU. So we need to get our X bar because we need to get the moment, right? You're gonna add X bar to the distance that we have, right? So first of all, we got that X bar, right? And then we get that Y bar. So X bar is equal to 10.4, right? But we still need to add that 100 millimeter because 100 millimeter is going to be that distance, right? So the offset from the force to the weld. So 100, and then you're adding to it this X bar. So that is your moment, which you are going to use in your secondary shearing, right? And that is so once we get our moment, right? Obviously, we need to get the radiuses, right, from the centroid to the weld that we're interested. So in our case, RA is equal to RB, right? And then this is simple geometry. We can get that. So 95 plus 56 minus 10.04 basically is to get the radius of A, right? And this is the radius of A over here. Right, so we're basically taking this guy, right, is going to be equal to this length minus 10 millimeter. So essentially, you're simply considering this triangle, right, to get RA. Right, so obviously here, right. So that distance here is like I said, 10.4, and then we're subtracting this total dA, right? So you can get this edge of this triangle, and then you can get RA like that. Okay. So let's come back to here. And so you get RA, RC, and then JU from the equation. Then we can get your the value of your secondary shearing, tau A double dot, and then tau B double dot. And you can get also tau C and tau D double dot in a similar manner. And basically here what you should do is we just do the geometry of this, right? So there are multiple ways of adding two vectors. The easiest way is, I'm gonna actually show you here. So in our case, basically what we had here is we had this guy, and then we had, this is our G, and then let's say you are calculating this point. So we said this is going to be our tau double dot, right? And let's say this is my tau prime. And in this case, and I want to give you guys a general approach, is here you just find that angle theta. If this angle here is theta, then this angle here is theta, right? And I can get a total value for tau is going to be equal to, in the x direction, let's say, it's going to be equal to tau prime plus tau double dot sine theta, and then tau y is going to be equal to tau double dot cosine theta, right? So in that case, tau is going to be equal to square root of tau x squared plus tau y squared. So this is the easiest way of basically calculating or getting that total shear, is you have to decompose this guy into x and y, and then this guy, in this case, is going to be in the x direction, and this is what you should do. And then this is obviously a general approach for evaluating these. Okay, so based on these, ultimately you can get the shear, the welding stresses at all the points, and in this case, it turned out that the highest stresses are going to occur at B, right? Where your total is equal to 37.37, and then at D is going to be the highest, right? Which is 44 MPa in this case. Okay, guys, so that is it. I'm going to be doing one more lecture on the bending of bending stresses in welded joints, right? And it's going to be basically very similar to what we analyzed today. Again, the key takeaway from here is you have to get familiarized with this table, and this table will tell you the type of the weld, get the throat area, get the location of center of gravity, get your centroid, sorry, and then get the moment about the centroid, and then get your primary shearing, your secondary shearing, and then add them up.